you want to share your screen?
Sure.
And just, yeah, take it away.
Okay, great. Is that working?
Yep, looks good to me.
Let me just see if my, can you see the cursor? The laser, I guess.
Yeah.
Great. Okay, let me start. So yeah, thanks to the organizers for inviting me to this great conference. I really like the format. It's like March meeting, but good. And I want to tell you about a new kind of development or follow-up work on topological defect networks. I should also thank Xiaogang for giving a great introduction, so I can happily leave out most of the introduction I would have already skipped for time reasons. And before I start, I also want to thank my collaborators on this work. So there's a grad student, Zijun Song at UC Davis, who's doing all the hard work, and Arpid and Wilbur, who probably many of you know and have met before, who are at Caltech. Great, so let me just dive in. The thing I'm going to talk about is related to this question, I think that was discussed earlier, which is about what kind of phases can these topological defect networks describe? And that's what this new work is about, kind of giving a positive result that at least all kind of code Hamiltonians can be described in this way. Let me step back a bit and say what these are. So hopefully you've already seen Xiaogang's talk earlier, where he introduced this idea of the sort of network of 2D states coupled together. We have a similar kind of construction we're calling topological defect networks, where this network can be actually like any network. It doesn't have to be this kind of quasi 2D one. Any network, and we're talking about 3D here, say. And we consider sort of a cellulation of the space with some structure given by the defect network. And basically it divides the space up into some cells. For the simplest case of like a cubic lattice, on this sort of 3 strata cells, we put in some kind of 3D topological quantum field theory. On the 2 strata, we put in some sort of defect surfaces that have topological deformability. So they're described by topological data in these topological quantum field theories. On the 1 strata where these things meet, there's going to be some one-dimensional defect lines that are also sort of topologically deformable, that are described by some data given by all of the various things meeting there, which you can actually do sort of a trick to compactify and treat as the boundary to a 2D topological phase. And then at the points, you have some kind of charge projector you choose. Okay, so why would you want to do this? I think the main goal for trying to use this formalism is basically that topological quantum field theory has been super successful at describing the universal characteristics of these gap topological phases in 2D, and to some extent the ones in 3D that are sort of this liquid type. And it sort of gets you the properties you want that are universal without giving you too much information. So we wanted to take this over to these new kind of non-liquid or fracton phases that for a while people were saying are beyond TQFT. But I should sort of give credit to, I think the first place we saw this conjecture was in Else Thorngren paper on sort of symmetry enriched defect networks, that actually for these supposedly beyond TQFT phases, there should be some kind of crystalline structure within TQFT that could probably describe them. And then the next credit comes to Dave, who really didn't give up on this idea after a few failed attempts for like more than a year. And being insistent, we finally found something that worked, which is this idea. And right, so what it does is it divides up these supposedly kind of complicated and seemingly ad hoc models into these topological pieces. So you can just sort of label each bit with this topological data you kind of know from TQFT, say, with defects in it. And then you can use these to build your fracton models without really having to reference a lattice. So in this picture I've drawn, there's this kind of really microscopic lattice scale, which is much smaller than the defect network scale. And one nice thing about this is that it kind of lets you get rid of this microscopic lattice scale, which is not a true continuum limit. We're not claiming it is, because you still have obviously this scale of the defect network, but it lets you kind of nicely take this limit where the pieces become topological and you don't worry about the lattice anymore, which I think Xiaogang called like fine graining. So you can kind of iterate that to infinity. Okay, and what can you do with these things? So yeah, the first thing you can do is you can use them as sort of a construction, which we hope would be kind of universal. But okay, there's already sort of a caveat to that, where we have these models that have sort of U1 degrees of freedom, and then you get infinite order fusion. So for the purpose of this talk, let's just say we do not consider anything with infinite order fusion sectors. So we're going to talk about like finite order. And we hope to be able to describe all of those in these sort of gapped TQFT defect networks. Another nice thing, so within the phases you can describe with these models, having sort of control over the pieces you put in and describing them with TQFT is nice versus a lattice model, because you can use things you know about the TQFTs to constrain sort of the properties of what these models can do, which can be useful, for example, if you're thinking about how they work as codes. And you might be able to prove, you know, something we're working on, like some bounds on how well they can do. Great. So what can we do so far with these? I think in previous papers, already we showed like a bunch of examples, like the X cube, cubic code 1B. And a lot of people ask why 1B and not Haah's cubic code, the original one. And I'll show you why that was later on. There's also this type 1 fractal spin liquid from Yoshida that I think Xiaogang explained pretty nicely. And then we had this non-abelian D4 panoptic or hybrid example, whichever terminology you prefer. I think also all these string membrane net models, which can be of this hybrid type 2, can be described in this formalism. And we have a bunch of gauge layer models that are also of this type. And what I want to show you now is basically a recipe to also describe all CSS topological stabilizer codes. So most fractal models we know are of this type. I think if you kind of the sort of gapped finite order fusion examples, this covers like a lot of the ones we know, maybe not 100% of them. But at the end, I'll tell you a small extension I think probably can lift that to covering all of them. Great. To explain this new recipe that's sort of formalizing the way we constructed these in the previous paper a bit, I want to show you the X cube example, which is always the best example to start with when you're doing fractons. So in the previous paper, we already had a defect network for this, which was come up with through some clever ideas that basically were trying to mimic or find an isomorphic sort of charge theory in this defect network to what the X cube has. And what actually works is basically putting 3D toric code on these 3 strata, some flux condensing smooth boundaries or pairs of these on the 2 strata. There's some kind of more complicated thing on the 1 strata, which I'll explain a little bit more later. And then you have some sort of trivial charge projector on the vertices. Our new kind of more formulaic approach to describing how this construction works is to think in terms of this gauging construction of fractons. So going back to some of the earliest papers on fractons from this newest round of interest, at least, there's this really nice paper by Sagar et al. That described, well, introduced the X cube model via being a gauged version of this kind of generalized Plaquette-Ising model in 3D, which due to its constraints has this like planar subsystem symmetry. So when you gauge this, which basically you kind of lift these constraints into degrees of freedom, and you lift the relations that these things have, so the products of these that give identity now become like physical operators. So I've drawn those in green. Sorry, let me just, yep. And then you have another term in the gauge model, which is essentially just enforcing that some local operator creates a cluster of gauge charges, these fracton gauge charges in this case, that are of the same type, the same shape as the symmetry charges in the ungauged model. So essentially, yeah, when you gauge for the purposes of this talk, oops, sorry, you get some terms that are basically coming from the relations, turning them into physical operators, and then you get some other term that's just implementing the pattern of gauge charges being the same as the pattern of symmetry charges before gauging. Great. So in this new construction, to try and turn this gauging thing into a defect network, what we do we start on the ungauged side, and we take a single, in this case, spin, which you can think of as a qubit, and blow it up into a really big block. So we just make this block, and it can be arbitrarily big, or arbitrarily fine-grained, if you like, with many degrees of freedom on this cubic lattice in this block. And on these degrees of freedom, you put in just pairwise ZZ operators on all the links of the cubic lattice, say. So you have this big cube. It's basically just a repetition code for this single qubit. So it has the same information, but encoded in a redundant way. And the idea being that when we gauge this is going to become the block of the 3 strata. Great. So in this example, we have no couplings directly between any two qubits. So this means that between blocks of these Ising models, we have no coupling terms, basically. There's just these smooth boundaries. Now for the one strata, in this example, we have these terms that couple 4 of these qubits. And these end up becoming terms that you can use the redundancy of this repetition code to rewrite these terms just very locally near the one strata, so that you don't get any non-local terms, which is something we want to avoid in the defect network. We want everything to be really ultra local on this like microscopic scale. Okay, and so you can use that to rewrite these sort of 4-body terms along the one strata in this way. And in this case, there are no extra terms around the 0 strata. So you're basically done at this point. You have this Ising model with these sort of usual Ising model terms in the 3 strata, and then these other square terms along the 1 strata. You basically gauge this, and now because you've added all these extra degrees of freedom, you have this big block of 3D toric code from gauging the Ising model in the cube. You get these flux condensing smooth boundaries from these smooth boundaries of the Ising model. And on these lines, you get these lines that basically allow 4 of these E charges from the 3D toric codes to condense there, which is just implementing basically the gauge version of this this constraint term. And then, okay, an important thing at the point here, you get some local products of these plaquette operators near this corner, which is going to be sort of local in this microscopic lattice scale, will give you these relation terms, which is quite important, which we'll see in the next example. I think for interest of time, I'm not going to explain this line defect better. I'm just explaining here how this line defect implements the gauge charge patterns. One thing I want to mention is, okay, so we've determined in the gauging procedure in the ungauged model what the charge pattern is near here. How does that fully determine the line defect? Basically, you just go and look at these M flux loops in the surrounding toric codes, and you just find some generating set for the maximum group of those that commute with the point charges, and those things also condense there, or they generate the condensate there. In this case, this sort of nicely allows you to see the mobility of these things being line-ons in the X cube, but that's not too important for the general construction. In the general construction, you basically just know that the thing you've created is in the same phase as the original model, so you don't have to check this, which is nice. Okay, so now to go to a more interesting example that was kind of a little bit hard for us to work out before, for a reason I'll explain to you, which is Haah's cubic code, which I think is the coolest Fractal model. It has this nice partial self-correction property due to having very slow dynamics. And its ungauged version is this kind of weird tetrahedral Ising model. So you have just qubits on points of the square lattice again. And now you have 2 different types of constraint terms, which define a sort of fractal symmetry. Here's just like a cartoon picture of a fractal in 2D. It's actually like a 3D fractal, the true symmetry. Okay, so when you gauge this, because you have 2 types of constraint terms, you end up getting 2 qubits per site. And the first term, again, comes from relations, producing these things around a cube, which gives you identity, and that gets elevated to a physical operator. And then the latter term just implements that the gauge charge patterns mirroring the charge operator patterns before gauging. Okay, so again, we can play this game. We blow up each qubit into this repetition code. There are no direct 2-body couplings, so there's nothing coupling these cells. There's no direct 4-body couplings around a plaquette. These couplings are all around like a cube, so there's nothing to couple these things together. But when we look at the cubes around a vertex, there is these 4-body couplings that couple them together. So we include those. We can now say gauge this, and something goes wrong actually. So what we find is, like, again, 3D toric code in the cubes. On the 2 strata, we get these flux condensing smooth boundaries because the boundaries here were smooth. On the 1 strata, again, what we get this time is actually sort of trivial smooth boundaries that are just decoupled for each of the 3 strata meeting there. And then on
Hey, Dom, just finish up soon, yeah?
Okay, yep. Yes, on the 0 strata, we have these charge condensations. But the problem with this is that we are only getting the sort of second term from the 0 strata. We essentially don't get this constraint term in a local way in the defect network, because you would have to take products of these charge condensations at different corners of the 3 strata, which is sort of non-local in this microscopic lattice scale. And if you kind of allow operators that are this non-local in the defect network, you could essentially just put 1 qubit on every vertex, and then the defect network would be saying nothing. So you really need to have this extra super locality constraint in there, or it's just vacuous. And if you do enforce this super locality kind of thing on the microscopic lattice scale, this ends up being unstable because there's some operators you've left out. And it turns out you can kind of add some local operators that end up confining the charges. So you've kind of created the wrong thing. You've created like a symmetry breaking model. So how to fix this in the last half a minute I have? It's actually extremely simple. You basically just have to coarse grain one more time, which you wouldn't think you would have to do because the qubit code is already just having interactions living on a cube. But you coarse grain one more time essentially to bring the relation term into being sort of ultra local. So here's some just labeling of the qubits on a site. You now end up getting 8 Ising model cubes from these 8 different things. And they have these 3 strata couplings because some of the couplings become on site. Let me quickly just run through the last few slides here. You end up getting some 2 strata couplings from these couplings that go between cubes. And you can kind of work out exactly what electric and magnetic charges condense due to these. You also get some 1 strata couplings due to these things, and you can work out again, here's an example of everything that condenses due to these, which is just some sort of Z2 easy algebra problem. And then again, you get something on the 0 strata. Okay, so with taking all these things together and gauging it, you end up getting this defect network, which this time is stable. You implement these E charges from all these E charge excitations correctly from all these various E charges condensing in the different strata. And now the relations end up being generated locally on this microscopic lattice scale, in particular around these vertices. Because basically what you've done by coarse graining is bring in all the terms that get involved in a particular relation to living very close to any given corner, and none of the corners have to be involved in the same relation. Okay, so I'll just leave you with this summary of how this new recipe works, and thank you.